Good morning, everyone. So, in this session, I'm going to explain about magnetic effects of electric current. So, the meaning of the magnetic effects of electric current is so due to the flow of electric current through a conductor, it produces the magnetic effect. Nothing but suppose if you are giving some electricity to the some conductor, that conductor now will be exhibits the magnetic properties. Nothing but it exhibiting the magnetic lines from one end to the another end, like it acting as a one magnet. Nothing but due to the flow of electric current in a conductor, it will exhibits magnetic lines, and that conductor now will be act as a one magnet. So, like which is having a two poles on the ends of the conductor, like on the ends of the magnet. Okay. So, here in this session, we are going to discuss about, we have some objectives like we have to know about magnet, what is the meaning of magnet, and what is the meaning of magnetism, and after that what are the types of the magnets we have, and then what are the lines, what are the properties of lines of force, what are the properties of magnetic lines, and finally we have some topic like magnetic field, what is a magnetic field in a conductor. So, here in this PPT, there is some questions like do you know anything about magnets, and list the types of magnets, and also do you know anything about electromagnets, have you seen any magnets? Okay, so like that we have. So, now going for the introduction to our magnet. So, here before 300 BC in Greece, a natural ore found known as magnesia. Okay, in before Christ, in 3000 BC, nothing but in before Christ 3000 years in Greece, country, they found a natural ore called as magnesia. Now, this magnesia is going to be exhibits the properties of attracting and holding some small pieces of the iron. So, whatever the ore this having is now called as magnetite. So, as shown in the figure, see in the picture we have the figure which is we called as magnetite. So, that chemical name is Fe3O4. Fe3O4. So, now about magnetite, the Chinese have discovered the peculiar ability of magnetite to point north. The Chinese marines gave the name leading stone to the bits of magnetite. They given the name for the magnetite, for the bits of the magnetite, like as it is a leading stone. After that, the leading stone now name was changed to the lodestone. Okay. After that, magnetism. What is the meaning of magnetism? So, the phenomenon of attraction of iron pieces by a magnet is known as magnetism. Nothing but suppose whatever the phenomenon we are discussing about attraction of the iron pieces by the magnet, that phenomenon is called as the magnetism. But what about the like here we are taking one magnet, that now that magnet is going to be attracting the some iron pieces surrounding it. So, whatever the phenomenon is going to be happen in this concept is now is called as the magnetism. Now, going to about magnet. So, magnetism we are magnetism is mainly a very interesting topic for us to understand the properties of the magnet, and also the properties of the lines of force, because it always attracting the iron pieces which are surrounding it, surrounding the magnet. Okay, that is a very interesting topic for us to learn about magnetism. After that, magnet. Magnet is nothing but it is a substance which possesses the power of attracting pieces of the iron is known as a magnet. So normally it is a one small substance which is having the property or which is having the power of attracting the iron pieces surrounding it. Now the points of maximum attraction are called magnetic poles. So for a magnet, so we have the some maximum attraction points. Suppose we are taking one magnet, that magnet is always attracting the iron pieces. But normally the magnet is having the property of attracting the iron pieces surrounding it. Now, so the maximum attraction points of the magnets are called as the magnetic force. Suppose we are taking one magnet, we are pulling or we are sprinkling the iron pieces surrounding that magnet. Now that magnet is going to be attracting all the iron pieces surrounding it, but the maximum attraction is going to be happen, or maximum concentration of the iron pieces is going to be happen at the ends of the magnets only. Nothing but at the ends of the magnet we have the more concentration of the iron pieces, because those points we are calling as the magnetic poles. So now always the magnetic poles are the two names that we have. One is north pole and as well as the another one is the south pole. Okay, already say magnet always having the two magnetic poles. One is north pole and another one is the south pole. Okay, after that, knowing of that magnet, suppose if a magnet is going to be suspended in the air, but it comes to rest in the north-south line direction. Suppose we are suspending one magnet in a air with a having some supporting thread. So then also be the magnet is always indicating the direction of the north to south direction. Okay. So the magnetic pole that which is pointing the north is called as the north pole. So whatever the magnetic pole we have which is always indicating the north direction is called as the north pole, and whatever the magnetic pole which is indicating the point that indicating the south direction, that is called as the south pole. Okay, it is very important to learn. So what, suppose we are going to suspend one magnetic pole or one magnet with some thread in the air position, it always indicating the in the direction of the north and south direction. But so whatever the magnetic pole indicating south north direction is called as north pole, and whatever the magnetic pole that indicating the south direction is called as the south pole. After knowing of the poles of a magnet, now we are going to learn about properties of a magnet. The two poles of a magnet have equal strength, equal pole strength. The poles of a magnet cannot be separated. Okay, normally we not available any single pole. Okay, but we can't separate the poles like one single north pole and one single south pole, because isolated poles does not exist. So that is the one property. And after that, like poles repel each other. Meaning is that like poles nothing but one is north pole and another one also be north pole. Nothing but two poles are same. In that case, they can't attract each other. And unlike poles attract each other, like one north pole is there and south pole is there, they both going to be attracted to each other. So here in the below picture we have the diagram. In the diagram, see here some of the pictures are showing about revealing the concept of the force of attraction and force of repulsion. of a bar magnets. So we are taking the two bar magnets. One is okay, both are having the two poles. Here on the left side of the picture we have the north and south, and on the right side of the picture we have the south and north. Nothing but here we have the two different poles near each other, nothing but two unlike poles. So when we having the two unlike poles near each other, so there is a force of attraction between them, because always they are going to be attracted. Okay, in the below picture, picture B, figure B, we are seeing that on the left side we have the south and north bar magnet, and we have the north and south bar magnet. Nothing but here also we have the two different poles near each other, like one is south, one is another one is the north. So that's why now both are going to be attracted to each other. So this figure A and figure B indicates about the unlike poles are going to be attracted. Nothing but so here we have the two different poles near each other. That's why those two are going to be attracted. And figure C and D, see the pictures. In the pictures we have the on the top portion C picture we have the two north poles near each other. So because of having the two north poles near each other and side to side, there is a force of repulsion, because those two are called as like poles. When we have the like poles near each other, there is a force of repulsion between them. And after that, in the picture B or figure B, when we have the south pole and south pole near each other, nothing but they having the two like poles near each other. Two like poles near each other, they are going to be repulse each other. That's why in the figure C and D, we are going to reveal tells that both like poles are going to be repel each other. Okay. So after knowing of the attraction and repulsions of a bar magnet, next now we are going to discuss about types of magnets. Okay, types of magnets, we have so many classifications, but we are mainly discussing on the depending upon the existing of the magnets, like natural magnets and size of the natural magnets are normally those are in the available in big sizes, like they are in larger sizes, and which are obtained from the mines. Nothing but natural ores like in the earth. Okay. Okay, now we are going to discuss about that one. So types of mainly on the natural magnets. Natural magnets are mainly available in the earth ores or natural ores, which are coming from the mines. After that, we are going to discuss about earth as a magnet. Okay. Normally, we are going to discuss about natural magnets like earth as a magnet. Nothing but normally this earth is now going to be act as a magnet. Suppose we are taking the earth magnetic field is similar to that of the bar magnet, which are filled 11 degrees from the spin axis of the. Hmm. Hmm. So in this picture we are seeing the one earth is there. So now the geographic north pole is a magnetic south pole. See here in the picture of figure 4, we have earth. Earth is now acting as a one magnet. That magnet is having the magnetic lines which are coming from downside to top side. So now top side of the earth is now acting as a south pole, and the downside of the earth is now acting as a north pole. That's why the top side of the earth is now acting as a south pole. The geographical north pole is a magnetic south pole. The geographical south pole is a magnetic north pole. So those now earth is shown as a magnet. So here in the picture 4b, we have the one magnet which is is similar to our magnet, so which is having south pole on the top and north pole on the downside. Nothing but this earth is now acting as one magnet, which is similar to our magnet. That's why we are showing them as on the top side we have south pole, on the bottom side we have the north pole. Then after we are going to talk about artificial magnets. So artificial magnets nothing but they are man-made magnets, nothing but we are making the magnets by our experiments, by our mechanism, by creating some experiments or by creating some mechanism. Nothing but artificially we are making the magnets. So that's why those are called as the temporary magnets. So temporary magnets nothing but in which the magnetism remains for short period of time. Nothing but in this type of temporary magnets, we have the magnetism for short time period. So, but in the case of the permanent magnets, magnetism remains for a longer period. Okay. Then go for the types of temporary magnets. Here, types of temporary magnets we are seeing here. So, in the picture in the figure 5, figure 6, we have two arrangements like having the one conductor. For that conductor, we are giving some electricity like a battery, so which is having this positive and negative supply terminals, and we are giving some electricity by this battery to that conductor. After giving up the electricity to that conductor, we are creating some magnetic field surrounding the conductor. Okay, now that magnetic field is now producing some magnetic poles on the ends of the conductor, and now this conductor is now acting as a one magnet. Okay, like that also here on the figure 6 also we have the one toroid shape, one circular shape conductor is there. That for that conductor we are giving some electricity with our battery, and because of giving electricity to that conductor, now this conductor is acting producing some magnetic lines surrounding that conductor. Inside of the conductor we have some magnetic lines, and surrounding the conductor also we have some magnetic lines. So by this with this now conductor is now acting as a one magnet. So temporary magnets. So figure in the figure 6, in the figure 7 also we have the solenoidal arrangement of the conductor. For that conductor also we are giving some electric current. So because of the flow of electric current to that solenoidal shape of the conductor, it will producing some magnetism, or producing some magnetic field surrounding that conductor. Okay, that's why it is also acting as some temporary magnets, and it will now acting as one magnet. So in the figure B, in the figure 8 also, we are giving some electricity with the battery to the solenoidal arrangement solenoid, and that solenoid now is producing some magnetic field surrounding that solenoid from one end to the another end of the solenoid, and also in the middle of the solenoid also there is some magnetic field is going to be producing, and it always acting as a one magnet, so which is having some north pole and which is having some south pole on the both end. So whatever the magnetic lines which are coming from the one end of the magnet is called as the north pole, and so the end in which the magnetic lines are going to reach, that end is also called as the south pole. Going for the types of permanent magnets, we are seeing some types of permanent magnets. So this is one bar magnet. Bar magnet is normally in the shape of the rectangle shape, and this rectangle shape bar magnet is consisting of the two poles on both ends, like it is having north and south poles on the either ends of that magnet. And now this magnet is similarly simple in the like shape of the rectangle, and which is simple one to carry for doing so many experiments. That's why it is called as bar magnet. It is in the shape of bar, nothing but normals. It is in the shape of normals bar shape. That's why it is calling as a bar. It is calling as a bar magnet. So that picture in the figure B, figure 9. And after going for the circular magnet is on the top side, top view we are seeing a circular shape, but on the bottom side it having some it is having some like our vertical arrangement, which is having some inside cutting one, and on the top side we have some circular shape. That's why, and on the bottom also we have the two ends. So that's why on one end is called as north pole, and the another one is called as south pole. So because of having this arrangement, it is called as circular magnet. and go for our Arsu arrangement. And Arsu magnet, in the Arsu magnet we are seeing in the shape of the Arsu, like nothing but it is like a Arsu foot. That's why it is called as the Arsu. And this Arsu is having the two ends. These two ends are having or going to be act as a magnet. That's why those two ends are called as the poles, and those poles we are we are calling as one is north pole and another one is the south pole. Okay. After that, ball-ended magnet. So in the case of the ball-ended magnet, we are seeing on the both ends of the magnet ball. On the two ends we have the two balls, and those balls are are having on the both ends of that conductor, and that's why those are called as a ball-ended magnet. Nothing but we are having the ending part as a ball. That's why it is called as a ball-ended magnet. And after that, we are having the topic of magnetism of a current carrying conductor. So what is the magnetism for a current carrying conductor? So suppose we are taking one current carrying conductor, by giving some electricity to that conductor. Now that conductor is going to be producing magnetism or producing some magnetic lines surrounding that conductor. Those magnetic lines are they are encircling the conductor, and a phenomenon was discovered by Oersted at Copenhagen in 1820. When a conductor carries a electric current, a magnetic field is produced around that conductor. So which is shown in the figure 13. So see in the picture, after giving some electricity to that conductor, now this current is going to be produced some magnetism or magnetic field surrounding that conductor. Is going to be explained by our greatest scientist Oersted at Copenhagen. Okay, that's why this is called as Oersted experiment. After that, we are going to discuss about current conventions of a current carrying conductor. Nothing but, so what is the current directions for a current carrying conductor? Suppose if the current is flowing towards us, nothing but outward, as we are going to represent that one by dot. Nothing but simply whatever, suppose a conductor is going to carry the current towards us, nothing but towards, it is flowing towards us, nothing but the current is coming out from that conductor, or current is going outward from that conductor. So that is normally we are going to represent it by a dot. Okay, suppose some current is flowing away from us or inward, that current, that direction we are going to represent by a cross or a plus or cross mark. Nothing but we are suppose the conductor is going to carry the current inward it or away from us, so that direction is going to be represented by the plus or cross mark, because it is carrying inside the conductor, inside the cross-sectional current carrying conductor. The conventional directions are for lines of force. Okay, now for going to learn about the conventional directions for the lines of force. If the lines of force is passing towards us, as we are going to represent by dot. Similarly, the current flowing directions also, what are the lines which are going from us, suppose the lines of force is passing towards us or outward, so now that direction is going to be dot, and the current which is the lines of force which are flowing away from us, nothing but the lines of force which is going towards conductor, towards the inside of the conductor, that we are going to represent the plus or cross mark. After that, Maxwell's corkscrew rule. Maxwell's corkscrew rule, normally it is like a screw we are holding the corkscrew. So in the going for explanation of the Maxwell's corkscrew rule, This Maxwell-Cox tool is going to be explained by holding the cork screw in the right hand, and it has to be turned in such a way that it may travel in the same direction as the current in the conductor. Suppose the current is going to be going away from us, nothing but the current is going to into the conductor. We are also moving that cork screw with our right hand. We are turning that cork screw with our right hand in such a direction that may be in the direction of the current. So now the direction in which the fingers move the moves which are shows that direction of the magnetic flux around the conductor. Going for explanation the right hand thumb rule. So this right hand thumb rule, so grip the conductor with our right hand with thumb outstretched parallel to the conductor and pointing in the direction of the current, the fingers then pointing in the direction of the flux. Suppose we are gripping the conductor with our right hand, the thumb which is outstretched and in parallel to the conductor and which is pointing in the direction of the current, and the fingers which are encircling the conductor, then those pointing in the direction of the flux. Now go for the lines of force and magnetic field. Okay, lines of force and magnetic field. Suppose in this topic we are going to do some experiments to show the magnetic lines. We have some experiments to show the magnetic lines. Suppose we are doing some experiment for knowing some magnetic lines. Okay, now suppose we are placing a permanent magnet on the table. So cover it with a smooth white cardboard and sprinkle steel fillings uniformly over the seat. The fillings set themselves in a curved chains between the poles. Suppose we are taking one permanent magnet on the table and we are covering with smooth cardboard. We are covering it with a smooth white board with smooth white cardboard, and we are sprinkling the steel fillings uniformly over the seat. Now the fillings are set themselves like in the curved chains between the poles. The figure 18 shows the conception of the magnetic lines of force. The stronger the magnet, the greater is the number of the magnetic lines of force. Suppose we are having the stronger magnet, that means the greater is the number of these magnetic lines of force. Suppose we are having the magnet stronger means, so in that case it having the more greater is the number of the magnetic lines of force. After that, magnetic fields. So we have different magnetic fields. One is the current in the wire. So in the current in the wire, we have the magnetic field in the form of a circle. For the case of the loop wire, in that case, the magnetic field in the like a circle on ends of the conductor, on both ends of the conductors, on both ends of the loop of the wire, and in the middle it is a straight line. For the case of the solenoid, on the ends of the conductor, on the ends of the solenoid, it is just a straight line, but in the top and bottom sides of the solenoid, we have the circle in shape magnetic field. But in the case of the Bohr magnet, also it is like a our normal solenoid shape of the magnetic field. In the case of the Earth, also it is like a similar to our Bohr magnet. So this is the different types of the magnetic fields we have for different types of the element of the current wires. Go for the magnetic lines of force. So the magnetic lines of force, it is always in the form of the circle or circular loop, uh, but they never intersect each other. Okay, now going for the what are the definitions? Some definitions regarding the some terms regarding our magnetism. So in that one is magnetic lines of force. So normally magnetic lines of force is normally we are defining in this format, like it is an imaginary line which is drawn in the path traced by a unit north pole moved freely around the magnet. Okay, what I'm saying here, suppose we are going to move the unit north pole around the magnet, whatever the imaginary line, whatever the path is which is traced by the imaginary line, is suppose we are going to draw that imaginary line path is going to be represented as lines of force, is indicating some path. Nothing but in the case of the one magnet, we are keep going to move the one unit north pole around that magnet. Now whatever the path traced by this unit north pole, we are indicating by an imaginary line. So that is called as the magnetic lines of force. Magnetic lines of force is in the format. So here we are seeing it is a one magnet. On that magnet, we are suppose we are going to move the one infinity in north pole around that conductor, around that magnet, whatever that line, whatever the path traced by that unit north pole around that magnet is going to be represented by the is going to be represented by some lines. That lines we are calling as magnetic lines of force. So going for the explanation, direction of the magnetic field. So now going to keep one, place a bar magnet rests on the table and place 3 compass needles as indicated in the figure. Okay, suppose we are keeping compass needles surrounding this bar magnet, and these needles are indicating the directions as shown in the below figure. Like the needles takes up the position such that their axis coincide with the corresponding chain of fillings. Nothing but their axis always coincide with the chain of the fillings. So whatever the fillings we are doing, we are did in that case, so they can the compass needles are indicating the directions. Now going for the directions of the magnetic field, the north poles are all pointing along the line from north pole of the magnet to its south pole. What I'm saying is the north poles are all pointing along the line from the north pole of the magnet to its south pole. The lines of flux are azimuthally pass through the magnet, emerge from north pole and return to the south pole. So what are the flux lines which are we are assuming we are those going to pass through the magnet? They are emerging from north. They are emitting from the north pole and they are going to return to the south pole. So in these two pictures, we are simply seeing that we are keeping one compass needles near to the one bar magnet, and their axes are going to be coincides with the corresponding chain of fillings. Nothing but the directions of the compass needle always coincide with the chain of fillings. Nothing but they are indicating the same direction of the chain of fillings of the iron pieces. Now going for a discussion about the properties of the lines of force. So in this topic we are going to discuss some properties regarding our what are the properties of a lines of force, what are the properties for the magnetic lines of force. So normally magnetic lines always start from north pole. So keep in mind that the magnetic lines are always started at the north pole and they are ends at the south pole. Okay, in the magnetic lines are always started from the north pole and ends at the south pole, and they are always form closed loops. Okay, the magnetic lines are always forms a closed loops. They never intersect with each other. So these magnetic lines are never intersect with each other, but they are not they are not always, they never intersect with each other, nothing but they never coincide with the another magnetic lines. And also they behave like a stretched rubber bands. Okay, normally they behave like a stretched rubber bands. Nothing but suppose we are stretching a rubber band with our finger, with our hand. So in that format also, in that format only, these magnetic lines are always behave, and they are unaffected by the non-magnetic materials. Okay, by using the non-magnetic materials, they are not going to be affect anything, because it is a one magnet. That's why these are not affected by the non-magnetic materials. Okay, remember here properties are very important for us to know about more thing about the properties of lines of force. So they are always started at north pole and they are ends at south pole. They form a closed loops, nothing but they are always keeping forming a circular paths. They are always forming a closed loops, circular loops, nothing but circular loops. They are always like a closed loops, and they never intersect with each other, nothing but they are not intersect with another magnetic lines, nothing but they are always in the direction of a circle. That's why they won't intersect with another circle, because they never intersect with another any lines, and also behave like a stretched rubber bands, and they are going to behave like a rubber stretched band. Suppose we are keeping in our keeping one rubber band with our hand, like that format only, these magnetic lines are going to be behave, and they are unaffected by the non-magnetic material. Nothing but they are, suppose we are going to use one non-magnetic material, so because of using of that one also, they won't going to be affect anything. Okay, and after that we are going to discuss about lines of force through the medium, lines of force through the medium, lines of force through the air. So suppose we are using the medium, in that case the magnetic lines which are traveling through the medium from the north pole to the south pole. In the air also, they are all traveling from the north pole to the south pole of the horse pole soup, soup magnet. Here we are using the one horse soup magnet also. In the horse soup magnet also, these magnetic lines are traveling from the north pole to through the medium to the south pole. In the air case also, the magnetic lines are traveling from the north pole to the through the air to the north south pole. And after that we have some definitions regarding the magnetic field and magnetic flux lines. So we have some terms, we have some terms, and we have some definitions regarding our magnetism. Like so, what is the definition? What is the meaning of magnetic field? And what is the definition of magnetic field? So the definition for the magnetic field: the region or space around a magnet in which the imaginary lines of force exists is called the magnetic field. Suppose we are taking one magnet. Around that magnet, we have some space or we have some region, so in which we are going to be having some imaginary lines of force. Nothing but suppose we are taking one magnet, around that magnet or a region around that magnet or space around that magnet, we are existing the some imaginary lines of force. So that is called as the magnetic field. What is the meaning of magnetic flux? Magnetic flux meaning nothing but the total number of the magnetic lines of force in a magnetic field is called the magnetic flux. Suppose in case of the magnetic field, we have the total number of the magnetic lines of force. That is called as the magnetic flux. The total number of the magnetic lines of force in a magnetic field is called as the magnetic flux. So this magnetic flux is normally is going to be measured in Webers. So 1 Weber is equal to 10 to the power of 8 lines of force. So here the magnetic flux nothing but in a magnetic field, the total number of the magnetic lines of force is called the magnetic flux. This is we are indicating by psi. The number of lines of force for unit area is called magnetic flux density. So this is the definition for the magnetic flux density. What is the meaning of magnetic flux density? The total number of the flux lines for the unit area is called as the magnetic flux density. That we are going to indicating by B, and it is measured in Weber per meter square, or we are going to indicate depended by the Tesla. So magnetic flux density is equal to magnetic flux per unit area. This is the formula for magnetic flux density, that is B is equal to phi by A. So this is what you understood about this topic of magnetism, magnetic effect of rotary current. So summary about this topic. On completion of this topic, the student is going to be able to know magnetism and types of magnets are, what are the types of magnets are there, and what is the meaning of lines of force, and what is the direction of the lines of force for the current carrying conductor, and after that what is the definition of magnetic field. So the magnetite chemical formula, that is Fe3O4. The magnetic flux is measured in Weber, and quiz is there. The conventional representation inward current is nothing but it may be plus or cross, and both A and B are correct, right? So D is answer. So these are frequently asked questions are there. What is a magnet, and the list of properties of magnet, and the list of types of magnet, and list of properties of magnetic lines of force. Assignment: map magnetic field for a bar magnet. Prepare for electromagnet. So hope you understood this topic. Thank you for listening.